Hello everyone. Sorry about the whole scheduling kerfuffle this week, but this is the video lecture for lecture number 6. So I'm going to do this in, I think, 2 parts. So the first part, we're going to focus on practicing choosing the best proof method. So we're going to practice using when do we want to use direct, when do we use contrapositive, contradiction, and we're also going to do proof by cases and then also doing a biconditional proof. And then in the next part, we'll do proofs using pushing definitions and also doing existential and non-existential proofs. So that'll be part 2. All right, so let's just go ahead and get started. So first off, let's look at this theorem right here. Let x and y be integers. If x plus y is odd, then exactly one of x or y is odd. So what is this saying? So this is saying, like, if you take any 2 integers, so for any integers, x and y, if when you add them together, you know that this is odd, then either there's one of two things that's happening, right? So exactly one of x or y is odd. So either x is odd and y is even, or it might be the other way around. X is even and y is odd, right? So they need to be opposites, right? Exactly one of them is odd, so the other one is going to be even. Now, direct for this one might be a little tricky. Direct is a really good thing to start with because often direct will work. But the problem is the conclusion, right? So we start with x plus y is odd, which is a little strange to have a sum be odd. So that's already something maybe direct isn't good for. So x plus y is odd. Like, what does that say about x or y, odd / even? It's not clear, right? Just because you have the sum being odd or even, not sure exactly what that says about the individual things. The other issue is that the conclusion has an or in it, right? So exactly one of x or y is odd. Anytime the conclusion has an or, it can be a little tricky to do direct. So I see the or and I think, okay, maybe this might be a good thing to do with contrapositive, because if we do the contrapositive, the or turns into an and ands are typically much easier to work with, especially when they're in the hypothesis. So let's try contrapositive. Now you could also attempt to do contradiction, but contrapositive is a good place to start, especially because, maybe we'll need to go back and do contradiction, but let's just start with contrapositive. So if we want to do contrapositive, well, what are we allowed to assume? So if we're doing the contrapositive, remember our statement P then Q becomes not Q then not P. So what are we allowed to assume? Not the conclusion. So the conclusion originally is exactly one of x or y is odd. That is, they have sort of opposite parity. So if we're doing contrapositive, we're allowed to assume that x and y have the same parity. That is, x and y are both even, or x and y are both odd. And you can kind of see this or, you're like, oh God, we have another or, but now the or is in sort of the hypothesis. So this is where we're going to be doing cases. So what do we end up wanting to show? Well, by contrapositive, we need not P, so not the conclusion. So we need to show that x plus y is not odd, which most people just say even. So we need to show that x plus y is even. Okay, that's not bad because we know how to show something's even, right? We need to show that it's 2 times some integer. So the main idea is we need to do 2 cases here. So the first case is when x and y are both even. And so that's going to be when x is like 2k, y is like 2j, where k and j are integers. And then when we add them together, we see that we get 2k plus 2j. And we want this to be even. So I'm going to pull out a 2, and I get 2k plus j. And this looks good because I got 2 times the integer. Okay. Now, the second case that we need to deal with, right, because x and y have the same parity means that they could both be even, or maybe they could both be odd, so we need to deal with the odd case separately. So x and y are odd, and then in that case, you know, we have x is 2k plus 1, y is 2j plus 1, and then when we add them together, let's make sure that we would get something even. So we get 2k plus 1 plus 2j plus 1, and then I can write that as 2k plus 2j, and then I combine the two ones and I get plus 2. Now this looks good because I got a 2 in every term, so I can pull the 2 out front. Yeah, so we get 2k plus j plus 1 in the end, and that looks good because k plus j plus 1 is an integer, and it's times 2, so this looks even. Okay, cool. So let's go ahead and write down our proof. Sometimes it can be hard to know where to start with a proof. If you're ever feeling stuck, it's like, how do I write down like a formal proof? Well, imagine you're like, your friend is confused and like, x plus, you know, I'm not sure how to show this result. Well, what would you say to explain it to them? So that's a good place to start if you're ever feeling confused. Okay, so there's different ways that you can, you know, stylistically write proofs. Alessandra has a really good one in the notes. I'm just going to write the one that I would write stylistically for me, and then you can kind of, you know, mix and match and pull which sort of style works best for you. So I would say, just to be clear to the reader, we proceed by contrapositive. Now, when we're doing contrapositive, right, we assume that x and y have the same parity. Okay? We want to show that they're both, that the sum of them is even. Okay? Now, we have two cases, right? Because we have, so the same parity that can mean one of two things, either both even or both odd. So we'll say we have two cases. So case 1, x and y are both even. So that's our first case. And then we can say, you know, we want to get this equations going, right? Because it's nice to work with equations. Like, we know how to manipulate equations, so we want to use them. So by definition, we know that x is equal to 2k and y is equal to 2j for some integers k and j. Then, okay, so we've got something that x is equal to, something that's y equal to. We want to say something about x plus y. So then x plus y, well, we can substitute. We know that x is 2k, y is 2j, and we can do the same sort of scratch work that we did right up here. So I pulled the 2 out, I get 2k plus j, and now that's looking good. And so I could say, so x plus y is even since k plus j is an integer. So you need to make sure you say k plus j is an integer, right? Okay, I think we're done, right? Because what we do, we started with x and y are both even, and then, you know, we wrote out this equation. Oh, look, this thing right here is 2 times an integer. That means it's even. We're done. Okay, take a minute, maybe pause the video and see if you can write out case 2, which is when x and y are both odd. I'll give you just a sec. Okay, let's look at case 2. So let's say x and y are both odd. Now, the sort of wording for this is going to run pretty similarly, right? So by definition, oops, x is equal to 2k plus 1, y is equal to 2j plus 1 for some integers k and j. So then, well, we want to say something about x plus y, right? So then x plus y, and now we're going to do the same sort of scratch work we did right up here. So we substitute, we get 2k plus 1 plus 2j plus 1. I'm going to combine the 1, so I get 2k plus 2j plus 2. I want to pull that 2 out, so we get 2k plus j plus 1. And that's looking good. So I could say, hence, x plus y is even since k plus j plus 1 is an integer. Very nice. So here's a question. Are we allowed to do without loss of generality? Because like this case 1 and this case 2, as I said, like the wording is really similar. So maybe we could have just like written one and said like, oh, the other is the same. Well, it's not, because I mean the equations are different, right? We end up with sort of different forms here. So like there are details that are different in these two cases. So we don't want to say without loss of generality. We really do want to make sure we write out both of these cases. Now we should really like conclude the proof with a sentence to like indicate to the reader like what we've done, right? Because if you say, case 2, in an integer. Okay, did we show the proof? Are we done? It's not clear. So let's write a concluding sentence. So you could say something like, thus we have shown in both cases that x plus y is even. And then you could say something like, hence the result holds by contrapositive. Again, this proof is going to look a little different from Alessandra's because I'm using slightly different wording, but all the pieces are the same. Okay, let's proceed and let's go ahead and take a look at the next one. So the next result is a little different. So we've got let m and n be in Z, so let them be integers. The product of m and n, so m times n, is even if and only if, okay, that's important. So we got a biconditional going on. Let me highlight that. Sometimes it can be nice to highlight the important bits of a theorem to really illustrate like what pieces are you working with. If and only if at least one of the integers, m or n, is even. I think the original wording is a little confusing to my brain, so I replaced it. So what is this theorem actually saying, right? So it's saying like, if you've got let me actually do this in color. For any two integers m and n, m times n is even if and only if, so at least one of them, m or n, is even. So like if m and n are both even, that's good. If m is even and n is odd, that's good too. If m is odd and n is even, that's also okay. Or like we just need one of them to be even. The only thing we don't want is if they're both odd. So one way we could rephrase this is if and only if m and n are not both odd. So sometimes biconditionals can be a little weird. It really does help to break them down into two conditionals. So let's practice that. So this P implies Q. This is often called the forwards direction. So we would say, so if M times N is even, then, M and N are not both odd. For the reverse direction, you flip them. So you would say if M and N are not both odd, then M times N is even. Okay. Now take a minute and pause and try to think about what sort of proof technique would you use for each of these directions. And I'm going to give you a hint. I think we're going to want to use two different proof techniques, one for each direction. So take a minute to think about it. Okay, let's talk about the first part, the forwards direction. So we say if M and N is even, then M and N are not both odd. That's a little strange because we have a not in there. So it would be nice if we could sort of, flip it around. So let's go ahead and just try contrapositive with this. Sometimes it can be nice to even just write out the contrapositive of a statement and see if it looks like it would be easier to prove than, the direct implication. So if we're doing contrapositive, we take not the conclusion. So we'd say M and N are both odd. And that's nice, actually. That's really nice, because if we're allowed to assume M and N are both odd, well, we know right away what those should be equal to by definition, right? So we have like really tangible things to work with. We don't have any like weird cases going on. And what would we want to show? We want to show that M and N is not, or M times N is not even. So another way to say that is M times N is odd. Okay, this looks like a nice thing that we can show. We've got two odd things. We want to multiply them, show they're odd. I think this is something we've done last week. So with the main idea, well, if M and N are odd, so we would get M is like 2k plus 1, and maybe N is 2j plus 1. And then we want to show something about M times N. So you do M times N. Well, what would that look like? 2k plus 1. 2j plus 1. I want to do this, I want to make it look like 2 times some integer plus 1. I want it to be odd, so let's go ahead and FOIL everything out. So I would get 4kj plus 2k plus 2j plus 1. And now I'm going to leave that 1 alone on the outside because I want it to be on the outside in the end. And I see that there is a 2 in each of these terms. Like there's a 2 hidden in that 4, there's a 2 there, there's a 2 there. So I'm going to pull the 2 out from each of those. And I get 2 times 2kj plus k plus j, and then plus 1 on the outside. And this is looking good because now this right here is an integer. And we got 2 times an integer plus 1, so that makes it odd. So that's looking really good. Okay. For the other direction, I think that we can just go ahead and do a direct proof. So if we're doing direct proof, what are we allowed to assume? We're allowed to assume at least one of the two integers is even, right? M and N are not both odd, so at least one of them is even. And what would we want to show? We want to show that M times N is even. Okay. So this is a little strange. So at least one of the two integers is even. So either, M is even or maybe N is even. And then we don't really know anything about the other per se. So let's go ahead and do this by cases. So case 1 will be maybe m is even, and then case 2 will be n is even. And in each of these cases, I didn't leave much room for myself here, but if m is even, well, then we know that m looks like 2 times k, and we want to show something about m times n. Well, let's look at m times n. If we do m times n, well, I don't really know what n looks like in this case, but I know what m looks like, so I can replace it. So 2 times k times n. Oh, but this looks good because we want to show this is even. So we have 2 times, k times n, and that k times n is an integer. So it's even. So that's looking pretty good. And then what about case 2? Well, case 2 is n is even, so then n looks like 2 times like j, maybe. And then m times n would be m times 2 times j. I'm going to rearrange this. I'm going to get 2 times n times j. Oh, that looks good because I have 2 times an integer, so it's even. Okay, so let's go ahead and write down this proof. Now we're going to have to do 2 different directions for this, since it's a biconditional. So I would say maybe, for the forwards direction, or maybe you could even just restate this right here. So you could say, first we will show if m times n is even, then m and n are not both odd. You could state that, and you say, then we'll prove by contrapositive. I'm going to just say, for the forwards direction, and then we proceed by contrapositive. That was sort of our idea. What are we allowed to assume? So we assume, what do we get to assume here? We assume m and n are both odd. Okay. What does that mean? Well, by definition, m is going to be, 2k plus 1, and n is going to be 2j plus 1 for some integers k and j. Okay. What did our sketch say? We wanted to show m times n is odd, and we were doing sort of this arithmetic here to show it. Okay, so let's go ahead and write down that arithmetic. So we could say then m times n is substitution 2k plus 1 times 2j plus 1 equals, and then 4kj plus 2k plus 2j plus 1, and then we wrote it as 2kj plus k plus j plus 1. Hence, or you could say maybe since 2kj plus k plus j is an integer, we have shown that m times n is odd, which is what we wanted. So this is really personal to me. Sometimes I really like including this in proof to really demonstrate that this is what we wanted to do. I sometimes say, so we have shown m times n is odd as desired. Kind of just an embellishment. Okay, I think that's the forward piece. Let's go ahead and do the reverse piece. So you could restate this statement right here. Sometimes I'm a little lazy and I just say for the backwards direction or for the reverse direction. You could say, because we did the first part by contrapositive, it might be nice to say to the reader that we're just going to do this directly. So we proceed directly, and then you could say by cases. Okay. So what's case 1? Case 1 was m m is even. So then we know that m is 2 times k for some integer k. Thus, what do we want to show? We want to show m times n is even, so we follow our sketch. So m times n is 2 times k times n, which if you want to be super clear, we can write this like the k times n in parentheses. So we've got 2 times an integer. So you can say which shows m times n is even since k times n is an integer. Okay? And then you could do case 2, and it's very, very similar. So case 2, n is even. Then n is 2 times j for some integer j. And then you can say thus m times n is 2 times k times j. Or sorry, whoops, totally getting ahead of myself. We don't know anything about m. M is kind of unknown in this case, but we know what n is. It's 2j. So we can rearrange, get 2 times m times j, and you can say which shows that m times n is even since, what do we got? We've got m times j is an integer. Okay, and that's the proof, right? So we did both directions just like we wanted. Now we ask ourselves, are we allowed to use without lack of generality here for these two cases? Because these two cases look really, really similar, just like the last one. The last one we weren't allowed to because the equations look different. In this last one up here, the equations we ended up with, we had like a 2k plus j, but this one has 2k plus j plus 1. So those are distinct because that plus 1 there makes it different. Here, they are basically identical. If you took case 1 and just everywhere you saw an m, you replaced it with an n, and everywhere you saw a k, you replaced it with a j, you would exactly get case 2. So this is a case where we are allowed to do it without loss of generality. So another way to rewrite this piece here, you could say, for the reverse direction, we assume without loss of generality that, and you could pick whichever one you want, you could say that maybe m is even. And then you would say then, and you would replace it with this piece right here. And then that would conclude the proof. And then you wouldn't have to write out case 2 with exactly the same wording, exactly the same equations, just slightly, just different letters, different variables. Now you might ask, like, when are you allowed to use without loss of generality and when are you not allowed to use without loss of generality? It could be a little confusing the first time you look at it. I mean, research level mathematicians have run into issues where they've used without loss of generality when they weren't supposed to, and they've had to, retract papers, and it's a whole big thing. It'll become clearer as you practice more and more, and if you're ever confused, like, you can definitely ask, like, that's definitely a non-trivial question, like, am I allowed to use without loss of generality here? If you're ever in doubt, a really good thing to do is just, you can like write out the two cases or go through them in your mind and ask yourself, if I just replace like an x with a y or just like a k with a j, can I just write the exact same thing with the exact same words, the exact same equations? If the answer is yes, that's a good chance that you can use without loss of generality. If the answer is no, you better write out all the details.